So I continue the timing coordination lecture and remind you of this special notion of timing. You know, the English word time, something is timed. It's kind of nicely ambiguous as a lot of English terms. There isn't actually an exact German equivalent for that, right? That's why we often tend to use the English word. So it means that a movement is somehow temporally correctly done, so that you arrive just on time, at the right time, at some planned time. It's particularly relevant when that's relative to something else, for instance, that you have multiple limbs and they are coordinated in the sense that you arrive at the same time in the same movement state for the two limbs. And it's also very relevant when you're trying to coordinate with some object in the world that you perceive, and the ball, you know, falls and you want to catch it just so your hand has been in the right location just at the right time. And I mentioned that that is always based on prediction, because movement control, motor control and planning always takes some time. There's always a delay between when you initiate the planning and when you succeed, and that will be a topic that I'll elaborate today. And so you need to make some prediction based on an internal model. So that's notion of timing. And I mentioned that in autonomous robotics, there is a long-standing tradition to separate the timing level so that timing is planned and coordinated at a level that is more macroscopic, macroscopic task related. And this so-called template anchor metaphor is more a mental picture, but that's been used a lot. I'll answer the question in a moment. And so that this is an attempt, in fact, to create a particular layer of internal processing at which you can do coordination and timing, and separate that ultimately from the control problems that also affect timing. And next week, I'll define more rigorously what control actually means. And what I'm talking about now is always assuming that somehow you can deal with that. That is, if you plan a time course at the task level to reach, you know, a certain target in time, that you can also succeed in actually physically doing it. That is, sending the correct currents to the correct motors so that they really generate the acceleration so you arrive in time. That's also a not trivial problem, right? That's a control problem. And so in classical engineering, we always assume that these things can be separated. In the nervous system, it's much less obvious. And that reflects itself also in the idea that the timing is at an appropriate level of abstraction, where you talk about, for instance, the body in space or the hand in space or something like that. While then the detailed time plans are sent for control to all the articulators, all the components, and that would then be something, for instance, just tracking a desired trajectory. So someone, Jonas, asked if coordination or coordinated and timed are different technical terms and what the difference is. So coordination is really relative timing, while timing is ambiguous with respect to whether it's relative or absolute. So absolute timing is sometimes important when you, actually, it's a good question, what is actually good for? But for instance, in conventional robotics, you would just want to be as fast as possible. But ultimately, actually, it's a good question. Absolute timing in a functional sense isn't really usually, you know, if you have a desire to do something at a certain time, but nothing depends on it, then maybe that's not a very interesting constraint. So actually, in that sense, relative timing, that is arranging that the temporal relationship between something, a movement you generate for one actuator or, you know, one robot compared to an object, or and also actuated, a different effector, which is coordination. That is really the functional meaning. So in that sense, you pick up something that absolute timing is maybe more an academic issue. I mean, humans can do it, and it's an interesting thing to study just per se how you do that. In robots, it might not be really so relevant. I hope that answers your question. In fact, I have this right here, so I just review that we use these four concepts from human movement. I'll take you through those real quick. So absolute versus relative timing, I illustrated with this extreme case where the intervals that different events that match onto each other here, the threshold piercing events, can vary. That variation would be a variation of absolute timing. How reproducible is the time that is needed to achieve a certain outcome? While the relationship between two such traces with respect to the event, so where is one event occurring in one effector versus in the other effector, that difference in timing, that's called relative timing. And that's really the functional thing that's important in most robotic cases. In periodic movement, you can measure that by relative phase. In non-periodic movement, you can essentially use the same. You use a relative time variable, and you can normalize it by the movement time. It doesn't matter that it's not periodic. And then you can also talk about relative phase, even though it's a single cycle to assess it. And so from this biological work, which I expanded on last week, there is the hypothesis that timing comes from underlying oscillators. They are, of course, thought to be neural in the brain, but we sometimes use equations that are not necessarily consistent with neurophysiology. And then they're just oscillators. And if these oscillators have periodic solutions, we call those solutions limit cycles. And we think of stable limit cycles, or limit cycles to which you converge if you're in the neighborhood. And that is actually the mathematical idealization of what clocks are, limit cycle systems. You read that in that paper that you studied probably, or still studying, and some of you were aware of that previously. The Hopf oscillator is, the normal form of the Hopf bifurcation. So it's a low-order polynomial. For a polynomial in polar coordinates is particularly simple. That is a model that in my group we have used a lot because it's so convenient. You can analytically compute the cycle time, the amplitude. You can control the stability by this alpha. The relaxation time is essentially 1 over alpha. So it's very nice that way. It makes harmonic movement. A couple of people have been using that. And in fact, I just yesterday had a very interesting session with the Intel research community, and they want to put onto their neuromorphic chip a Hopf oscillator. It was really very attractive to have that as a analog hardware, hardware base for that. And while usually they have just the spiking neurons. This neural oscillator is reviewed in the paper that you've been reading. That's the generic pair of excitator-inhibitor neurons that are coupled reciprocally. So the excitator neuron drives the inhibitor neuron, which in turn inhibits excitator neuron, and some self-excitation plays a role. And these systems have limit cycles, and the exercise invites you to actually play with that and make sure that you understand why that happens. So the key idea of timing being generated by oscillators is then that relative timing can be achieved by coupling oscillators. So if you are talking about two active systems that you generate time courses for, that would be just mutually coupling those. Or you could talk about one time system that is coordinated with something external, like a perceived time course that you estimate from perception. And that would be then input that effectively couples that dynamics. And these are the two cases, coordinating limbs or articulators versus coordinating an action with a perception. So in that paper that you also studied, this shows up in, for instance, one of the oscillators U2 coupling into the equation of the other U1 and vice versa. And you can have more complex couplings. I just took out this, here's a contribution to the inhibitory system, but you could also imagine that you couple in other forms. And what that does is that it tends to align time courses. So if these two oscillators are going, then they will tend to synchronize. There's actually very cool, cool pedagogical videos on the internet about synchronization of oscillators, a couple of physical experiments, just some metronomes that are mounted on some flexible base, and then you see spontaneous synchronization. That's based essentially on coupling like that, where the movement of one metronome moves the base and therefore couples as a driving force into the equation of the other metronome. So if you have some time to idle away, Google that and you will find very nice demonstrations where a couple of oscillators like line up like that. So that's the general picture. And I took you then through one example of how we can use these ideas in robotics. This was one of our very early examples. This was a pure simulation example where a simulated robot arm intercepts a ball. And the notion was that it has an oscillator in here. This would be an oscillator. It is an oscillator. In this example, it was an oscillator for the position of the arm. It has this Hopf equation from which we can control the amplitude and the frequency or the cycle time. And then there is an initial state that's a fixed point and a final state that's a fixed point. And what we would do is make sure that when we reach the final point, we turn off this term by multiplying it with a neural variable that is then 0. And the final variable u is on. We start the whole thing by turning the neural variable that stabilizes the system in the initial fixed point off, making this 0, and turning the Hopf on. And these were the equations that we used at the time. This is a third order normal form equations with a pitchfork bifurcation. It's not what we know from neural systems, which have sigmoids, but it has the same qualitative dynamics. And therefore, what it can do is if the inputs to that system change, it will switch the movement off, on, the initial fixation off, and then at the end of the movement, it switches the movement off and the final state on. And you achieve that by these inputs to this switching dynamics, which we call the quasi-booleans, because they are tend to be at 1, 0 or 1, but then they have transition functions. So these functions are sensitive to the state of the oscillator. And I didn't go through the details of that. So a system like that can can start a movement at a certain input. The input was the perceptual signal from the ball that it would catch was all simulated. And what happens here is that there is some sensitivity of that input to the perceived time to contact. We added noise to show that it's robust against that. So these quasi-booleans here, for instance, switch when time to contact reaches a critical level. And the parameter of how fast the movement takes is tuned such that at that time to contact, the system would just achieve the movement in the time that remains. The model here consists of assuming time to contact is an estimate of how long the time to contact is if the ball continues with constant velocity. That's a very well-known concept in a lot of driving models, and driving assistance systems use that kind of notion to control, for instance, braking. It has the advantage you don't really need to estimate distance. You only need to estimate that time to contact. And you can actually extract that information very directly from some sensory information. For instance, how quickly the ball looms, as we say, how quickly the ball on a vision sensor grows in size. You can just talk about the percent growth. You don't have to know how large the ball is or how far it is. Just if you see the time, for instance, for it to double, from that you can directly estimate time to contact if the ball is moving at constant velocity relative to you. It's a very attractive kind of concept. So that's why we use that. So that's an example of coordination, right? It's a coordination of your hitting movement with that visual time to contact. So today I wanted to explain another example that's in a sense more sophisticated. That last time I had not enough time to elaborate. So this is an example that where we use a vehicle. So this little thing is one of those mobile robots that you've seen in the first part of the course. It's a Kepler, I think, at the time, running around an arena. We had some target that it was achieving. I believe that this system, we actually had programmed the target in terms of dead reckoning. It knew where the target was. It doesn't have any sensor information about the target. It had distance sensors, so it could do obstacle avoidance. It did the obstacle avoidance in the style that you learned at the beginning of the course. And I'll show you the equation in a moment. And so the task we set ourselves here is to say, we want to control the speed of that vehicle. So how fast its wheels are turning, the average of the two wheels, to make sure that it arrives at a particular time within a particular, so it's precisely within a planned time interval. We did that again using a Hopf, so making even a kind of nice time profile. We assume that the vehicle is controlled so that it can really realize the wheel velocities that we command, and it's a good approximation for that vehicle on a smooth ground. Has nice servo motors. It can actually do that fairly well. And so the question we ask ourselves, if the kinematic path planning here with obstacle avoidance creates a longer path, then the assumption of of how we generate here the time course is no longer valid. And the velocity profile here depends on the initial distance, right? You have to say, I want to cover this distance in this much time, and that gives us a particular velocity profile. And so that is no longer true because the path effectively is now longer. And can we update the velocity of that robot to still arrive at approximately the same time? I mean, it's not going to be perfect, but to reduce the delay at which the vehicle then will arrive. So if it were to just keep constant velocity, it would of course arrive later if it has a longer path, which is the thing humans also will do. So that's like an academic task. It would be better to do that with a robot arm and so on, but it was actually easier to do it this way. So here's some ingredients. This is not in the old slides. So the heading direction of that vehicle is steered in the way you're familiar with. The target term and obstacle terms from its sensors, nothing special there. The only thing is that the velocity, which is here this variable a, has this equation, and that is an equation that at its core has a Hopf oscillator, written again here, and again has an initial term and a final term. That's initially you're sitting at a equals 0, there's an attractor at a equals 0, b is just an auxiliary variable to get the oscillator going. So you sit initially at that off state, and then by manipulating these neural variables here, we use the square of the variable rather than the absolute value, because the neural variables here can change sign. So they're not like from 0 to 1, but from -1 to +1. And 0 is off, and plus and minus are on. So this is turned to 0. It's initially 1, and then it's turned to 0. This one turns from 0 to 1. The oscillator starts, and then at the end you turn this off, and then you have turn this one on, and this one has an attractor at the final location of your timing variable, which you can compute. That actually will be 0 if it's unperturbed, and it will be some other special term if it's perturbed. I can't explain that in detail, but it's sort of the final state of the trajectory. So that's the velocity profile, and there are so the Hopf oscillator, you have the omega right here that determines the cycle time. So we're determining a particular, imposing a particular time at which we want to arrive. So the time we allow that robot to take, I have to make sure it's something that it can physically realize. And then what we have to do is we have to compute the peak amplitude. So if you think of that, this shift here of the coordinate frame, it amounts to the peak velocity. If a is velocity, the peak velocity that system will have. I think it's maybe half the peak velocity. I don't remember exactly. And so what you have to do is you have to say, given a certain distance, and distance at t equals 0 means that in your initial position, you estimate how far you are from the target with a straight line movement. That will be the amplitude of the movement. So at a certain distance and at a given cycle time, what peak velocity do I need to arrive to cover that distance in that time? If you think through that, you end up with this expression. So this is based on the movement being sinusoidal. So you have know exactly the solution, sinus omega t, and you can figure out, if I want my solution, that's the integral, the Hopf returns to velocity. I need to integrate over that to get the position, integrate over that, find out what parameter I need for the amplitude of that velocity signal to arrive at the target at that time. So that can be engineered, right, easily. Now, briefly, how we switch. It's the same idea that we have this kind of neural dynamics. It's again this funny form of a pitchfork bifurcation where these different U's compete here. So these A are the other. Let's say if I take one of those U's, the other two contribute a negative term here, so that if any of those is on, it suppresses the one I'm looking at, and only the one neuron that is on, it doesn't then get competition. So this leads to a single one of those three neurons becoming activated. So for instance, during a typical movement, you would have this sequence where the postural state is active, the first neuron, and then it goes off and the Hopf comes on, and then in the end, the Hopf goes down and the final state comes on. And this is a case where there was some perturbation, which I'm not explaining here. So the trick about how this does, this would do absolute timing, right? This would ensure that the trajectory is such that you arrive at the target at the right time. The notion that you really coordinate would now be that if you perturb the system, that it corrects the parameters of the timer to restore the original arrival time. So the perturbation here was from obstacle avoidance. So what we assumed is that the system senses its current distance from the target. And then we figured out from the solution of the Hopf what would have been the initial distance the system would have had if it was currently, if at this time it was currently at the distance it was. So for instance, if it makes a longer path than originally thought, then at that time you still have a larger distance from the initial position and to the target. No, from the current position to the target, and therefore you're saying, well, if my plan was to be at the target at capital T, and I'm here at this time, then my initial distance must have been at some other position. And you're using that to then compute what peak velocity you would need from now on, and given that you have covered this much percent of the path at this larger amplitude, what peak velocity you now need to reach the target in the remaining time. It's a little bit complex to, you see, this is based on the exact solution of the Hopf equation. So this comes from the integration of the velocity. It's no rocket science. You can easily sort of go through that paper and correct that, compute that. So that enabled that system to react to these delays. So for instance, here in the phase plane, this is the Hopf oscillator, B versus A. The unperturbed movement would be the green one, and the perturbed one would be the red one. The perturbed one, meaning, in other words, the one that would take the same amount of time to cover a larger distance would be the red one. We need the larger speed to cover a larger distance in the same time. So here at this point, the perturbation occurs through obstacle avoidance. And what the system then does is update the frequency, the variables of the Hopf. It does that in time, always at every moment in time, it updates that. And the blue line is this updated trajectory. And that's the way the system will steer. And you see that here you see the distance and the velocity profiles that result from that. Let's say if from the start you had that smaller distance, you would take that peak velocity. If you had from the start this larger distance that obstacle avoidance imposes on you, you would follow that red curve. In reality, you only notice here that you're now delayed through an obstacle, and now you're switching over to the red curve and updating at every moment in time the distance you would have. So you can say switch to the red curve. Only in the end will you be close to the red curve, and you will have some other parameter values in between that then generate this blue curve. And as you see, that succeeds in now covering that larger distance in about the same time as originally planned, the shorter distance, and of course at the cost of driving faster. So the limit is that you have to be able to drive as fast as that. There will be a limit where you can't do that, right? So that's what is actually happening here. So when the system is avoiding the obstacle, makes this longer path, it starts to accelerate to arrive at the same time. Here's some data from that paper. So we varied through the obstacle avoidance the total distance driven from 72 to 110 centimeters. So it's quite a bit. It's like by 30%. And we succeeded in keeping the movement time quite constant, right? This is very good. And the increase, is up to a factor of 1.5. You see, we're really managing to do that reasonably well. The limitation on that robot was really the estimate of where it is, what the remaining distance is, and that's based on that reckoning, and there are errors in there, and the control also, of course, is not perfect on that robot. So that is compensating for lost time. That would be timed movement. It's in a sense absolute timing, because we don't really have a physical thing to coordinate with, and the target is just an internally stored thing. All right. So in that sense, it would be absolute time. So I wanted to. So these were our ideas. So we were the theoreticians in this domain. I wanted to show you the state of the art. So I've never really been in the business of really building concrete competitive robot systems. I have had a lot of interaction with someone called Aude Billiard, who is a brilliant engineer in Lausanne. And I'll show you in the next slide, actually, work that comes out of her work with her former husband, Auke Eisbert, that also carries some of the ideas that we've proposed forward. This is an example that's much more impressive in a way than our little robot vehicle. But what you'll see why I'm not in this business, because it requires solving a lot more problems. So to actually get this to really work on real robots, you have to solve a lot of problems. So Aude had this very cool demo that she presented also at ICRA in Karlsruhe, maybe in 2015 or 16, I don't remember exactly. It's a robot that can catch an object in superhuman performance, so better than humans. I'll show you a video in the end. The robot demo was not working with the iCup, because the iCup actually really sucks. It was using the robot arm we have in the lab, the KUKA compliant lightweight LDR, lightweight LWR, lightweight robot, I guess is the name of it. So what happens here is that there is a perception system. It's actually mounted somewhat separately from the robot that observes an object. I'm not even sure, it might be it has some trivialized vision, so I think there are markers on the object. I don't remember exactly. So that's one part, and then it plans a catching pose, which means a location for the catch and an orientation of the gripper. It's a plan that it keeps updating, because it makes a prediction of how this thing tumbles, and then it keeps updating that plan. That's really cool. Right? That's really coordination, and make sure that the arm actually reaches there. That's really challenging task. So there's a lot of things that you have to do right to do that. I don't want to explain it all, but just to give you impression for all the things you do. You have to have, from your vision system, again, the vision is trivialized in the sense there are simple features that allow you to detect the object. The background is made homogeneous and so on. But then you have to model the motion. That is, you have to make a model that can predict the trajectory and thus get some pose estimates from that. See, that's done at high frequency to track the system. Then you have some models that tell you how, so the models inform the trajectory prediction. So it's kinematic models, it's models about how to, so for instance, you have a cylindrical model, object model, and you have some idea of, given the parameters of how the cylinder is oriented, what would be the grasping pose for that. I can figure that out. So that will be here in the reachable and graspable model. And then you also have a model of how the arm would be kinematically controlled. It's actually not about, again, the control is conventional in this system. And so when you get this posture, you're solving inverse kinematics. You have to ultimately control the model. That's a high frequency loop to control the robot. Somewhere in here, it's actually exactly in here, is the timer. And unfortunately, I can't fully explain that. But what it amounts to, it's called coupled dynamic resistance approach. That is, you have different time course generators. In this case, actually, It's all in a learning form represented by Gaussian mixture models. And you align them in time by coupling, by mutual coupling. So it's just a demo that the coupling can exactly make sure that two trajectories tend to be aligned, which wouldn't be aligned without coupling. So it's more complex than I can explain. This is required. It's all parameters are adapted through learning algorithms. And I just wanted to show you that that works. Actually, the link doesn't work that way, but I'll just copy that over. So you should be able to see this now. I don't know, do you hear this? Let's just have a look at these. They explain now a lot of features, but maybe these should be very cool. Yeah. I hope you saw that. Did you see that?
Yeah, we saw it.
Pretty cool, isn't it? I mean, these are, I was in the lab and I saw demos. Of course, it doesn't always work. In the paper, the report is like a 60% or so success rate and so on, the limitations on the pose estimation. And really, actually, hand has to grasp it, right? So they often use slightly deformable object like this plastic bottle where you can squeeze the object a little bit so you don't have a lot of problem with this bouncing off your hand and so on. So there are a lot of problems like that, but it's certainly one of the coolest demos I've ever seen in this domain. Good. So that uses this idea of coupled oscillators, but it is just one little component hidden in a lot of systems that has to do a lot of other things. And it turns out that the parametric tuning for this to be right is so complex they don't do it by hand, they do it by learning. And I don't explain really how that works. So the last example I want to show is sort of a poor man's version of this, which we actually did. We did this a little earlier, but poor man's where you can see this robot is not as fast and cool. It's also really not a very good robot. So it's our old robot. So we made everything slow. What's different, so it does something similar. It intercepts a ball and it updates online the movement parameters to intercept the ball. The added feature I want to illustrate here is also does really behavioral organization. That is, it can abort a movement and restart it and so on. So it autonomously does the sequence. The other one really just is ready, and then when it detects the signal, it will grasp, and it doesn't do anything else. It's not cannot decide on its own. This is a robot that in principle could be doing this forever, and will be starting a movement whenever it's right, and will be stopping to do it whenever the ball's out of reach, and it has a baseline that it returns to. We had a little feature where we had the robot start from the baseline and intersect the ball that was running on an inclined at a certain hit line. And so whenever it thinks the ball is now gone or is no longer in reachable space, it would move back to the baseline. The original idea was that we would have some time to accelerate, because this robot is so poor, it can't really accelerate very strongly and therefore not hit the ball very strongly. That's why we had this very soft inclined plane so that everything is slow. And you will see it doesn't really hit the ball very well. But that also gives us an opportunity to demonstrate this behavioral organization. For instance, you can see that the robot gives up if the ball is reflected and returns to baseline, and then it can reactivate and still arrive in time from wherever it currently is to hit the ball. So at the core of the system is the same kind of idea. So at the core is a timing signal, again, a Hopf with the initial posture, and there is a final posture, which I don't remember why it's not written here. And again, we compute from the distance to cover the cycle time that we give the Hopf oscillator. So the omega is 2 pi over the cycle time. This omega is directly determined from the distance to cover. And so we can adjust that, right? If there's perturbations, we can adjust that distance to cover. So this is simpler than this TUMA project that I just previously showed, because here it doesn't try to recover the lost time. It just tries to arrive at the right time. So it doesn't, it is not as good as in the other case, let's say. So it can also tolerate only smaller deviations from the programmed initial time, but it still goes in the direction of slowing down or accelerating to come to the meeting point at the right time. This system has now really a neural behavior organization. So those who listened to me in the winter semester will recognize some of those things. So in here are extraneural fields and condition of satisfaction fields. This is an intention node. This is a condition of satisfaction node. These different nodes are linked through what we call precondition nodes. So there's a sequence of behaviors like update a plan and move and fixate and different combinations of that. It's actually hierarchical. You have move to ball versus move to baseline, move the hand forward, move the hand backward. These are different behaviors that are activated under different circumstances. And all of those things are emergent just from these coupled dynamical systems. So each little circle here is a dynamical neuron, which is not a pitchfork, but it's an Amari type of equation that can be excitatory coupled or can be inhibitory coupled to other neurons, so positive and negative influence on the growth of other activation variables. And they tend to have bistable states that we can use to turn on and off with some stability regime. And we can wire this whole thing up to reflect certain behavioral principles. Now, the principles or rules essentially dictate under which circumstances would I activate which elementary behavior. This could be a unit of the elementary behavior down here. EB stands for elementary behavior. And then you can have at higher level, this elementary behavior activates that whole module, which is a sequence of 3 elementary behaviors. And again, this module is a combination of 3 and the same here. So you can perhaps imagine how that works. I'm not giving the very precise detail. This gets sensory feedback from the scene. There's a camera on that robot, and that camera, you see here, and that camera will track the ball, and the ball parameters ultimately control the behavior organization here. So you will activate the move to ball if that perception about the relative velocity of the ball, or it's actually, again, time to contact, that is within reach, then it will start to disinhibit the move to ball behavior, and it will engage all that. These variables also play a role in detail in some of the behaviors to depend in detail on the estimate, like the Hopf oscillator, depends on that. And so you hand that information to the individual components. So for instance, in a normal case, let's say we shoot up the ball on that inclined plane, the ball will go up on a parabola and then return. And if we put the rack in the right location, we will reflect it back. So the camera is always tracking the ball. This ball has a simple color on white background. So the vision problem is very simple. We have a Kalman filter in there to make a motion model of the ball. So from that, actually the elevation in the picture is a measure of distance. So we can very easily compute time to contact from that. And so whenever the time to contact comes within a critical limit, we're initiating a movement. So for instance, here at this point, a movement was initiated based on the estimated time to contact, where the racket moves to the horizontal position where it expects the racket, to the hit line here. And then at another critical position, it does this hitting motion. So this little path here, that's part of the hitting motion. And once it's hit, it returns to baseline. That would be a successful reach. So for instance, here, there are 3 degrees of freedom for the racket, horizontal. This is, I believe, vertical, and this is the racket angle. And because of the poor robot, this wasn't moving so dramatically fast. And so the hits are a little bit weak. So the important thing is that this would be always coupled to sensory inputs. So for instance, the ball is moving toward a location. The robot, if there wasn't this deflection by an obstacle, the robot would take on this position at that in time, position the racket here to reflect it this way. But at a certain point in time, which is about at this point of the path, the ball is reflected off an obstacle, and all the parameters are updated to then hit the ball at a corrected time, so a different moment in space, and still arrive just in time to make that hitting movement. So this is sort of like old billiards, except our system is actually much simpler. So we can really analytically know why it does that and how it does that. And of course, then it's not as robust, perhaps, because we didn't do any adaptation of parameters through learning. So here's a demo of that. It's very slow and hits the end. I don't know if you see that initially, so the demo is much less impressive than hers, but you see here that originally the robot, this was the baseline, and the robot was now planning to intercept the ball somewhere here. It's moving back. See that? It's moving back. And then the reflection happens, and now it updates and moves forward to hit the ball, right? That's what is flexible about that. And so this robot would do that forever. So it is totally autonomous. It doesn't have a start and end state. It just will always have one of those states. It's at baseline or moves or that's sort of the cool thing. Now, more complex situation, again, this is the unperturbed case. A more complex situation is here where the complicated configuration of obstacles, we'll see that in a moment, makes that the path is reversed so that the robot decides at some point that it will not be able, that there is no time to contact, that it will not reach, and therefore it returns to baseline. So here, initially it prepares to intercept the ball somewhere here, coming down here. It would intercept it somewhere here. That's this movement. At this point, it detects that there is no time to contact within the limit, so it returns to baseline. That's its movement, return to baseline. And then the ball, is again returning and has some predictable time to contact, and it plans a new movement that would actually be somewhere here. And there's another reflection, so it has to update in the last moment and still hits correctly. And that demonstrates not only is the timing adjusted, but also the behavioral organization. Not going into the detail, but you see that there are different behaviors activated different ones time in response to these perceptual inputs. Okay. So here's a demo of that. So again, it's not so spectacular to look at because of all this limited movement of the arm. I'll show you that initially the robot is, here, it's moving to intercept the ball somewhere here. And the ball is now reflected. And now it estimates there's no time to contact. And so you see now the arm returns to baseline. To baseline briefly. And then it actually finds a new interception and it goes there. Yeah. So even though the hardware demo was a little limited, it was heroic work by Farid Ubati because we didn't have a lot of infrastructure. So he did this very well. But it's a different thing to make this demo impressive. But the concept is one that there is here really the coordination of the time course itself, but there's also coordination in making the decisions just in time. And these two are related because if you're making an updated decision, you now have to make sure that in the remaining time you will actually hit the object that reach the event that you want to reach. Okay, so this is the end of this first part of the lecture, the second part of the timing lecture, where the theme was essentially that timing and autonomous robotics is best framed as a problem of stable oscillations or oscillators and their coupling.